Clearly, we're not going to turn in that pretest.
Yeah.
It's part of a package. I just wanted you to think about those ideas. We're going to talk about the answers to that pretest during today's lecture in a moment. I just want to point out the homework, selected problems 122, 124, and 121 star. Remember, the numbering got messed up in the selected problems booklet. 117 to 126, those numbers were used twice. And so 121 star is the second problem 121. We've already done the first problem 121. Everyone got that? Now, to give you something to do over the weekend, the solutions to the homework are over at Cards and Copies, as is the solution to that third midterm, the sample midterm. If you get bored, we have an exam coming up, yes.
Next Thursday?
No, actually, it's not until the week after next, okay? Yep. Now, folks, calm down. The voltage model, I just love teaching the voltage model. It's just so simple and so elegant. You know, if you see it correctly, if you see how all the pieces fit together, it's almost trivial. And the nice thing is that once you see it, once you get it all fitted together in your mind, it's like that dog in the dots. You can't stop seeing it for the rest of your life. You look at a circuit and it just jumps out at you. Now, if you don't see that dog in the dots before the midterm, it's just going to be a miserable experience. You see that dog, and I promise you, the midterm cannot seem hard to you. Once you see this model, once it's part of you, you can't not get it. Okay? The dog in the dots. You weren't in 205 with me?
No.
Okay. I'll talk to you later about that. There's a dog in those dots. We found a few, just not very many, a few key ideas. First of all, voltage, one way of looking at it is the amount of energy that is handed to each coulomb of charge as it goes through the battery. And then that energy is taken away from those charges as they then go through the bulbs. And that's kind of the way that the battery gets the energy that causes the filament to get hot and to glow, how it gets that energy from the battery to the bulb. It starts out as chemical energy in the battery. It is transformed to electrical potential energy that is then delivered to the bulb. Another way of looking at voltage, we talked about this last day, a more gut level approach, is oomph. It's the oomph, the push, the drive, the how hard you gotta work to get the current to flow through a given element. Technical. The two big ideas that you would be using, and the tools that you would have in your toolbox in a voltage model, are one, the brighter the bulb, the more volts across it. More volts, more jolt. And the second is, what goes up must come down. In other words, if I go around any single closed path, I'm going to say that again. If I go around any single path, and I left out the word closed because I didn't want it there before. If I go through any single path from one side of the battery to the other, the voltage has to add up to the battery voltage. The increase in potential that the charge gets as it goes through the battery has to be compensated for by a loss of potential as it goes through the bulbs. In other words, around any loop, the voltage rises and drops must be equal. I didn't say that well. Do you understand what I mean?
Yeah.
Okay. One of you do. Now, I'm going to just briefly review some of the things we covered rather quickly at the end of last day. In this circuit here, we were able to compare all of the bulbs except for B and D. B and D we just couldn't do with the current model. We had all of a small pizza, more than half of a large pizza dilemma. If I use a voltage model and I say that that's a 12-volt battery, I look down this path and I see two bulbs that are glowing just the same, just as bright as each other. I know they have to have the same number of volts. I also know that those volts across A and B have to add up to 12. That only gives me one choice. They got to be 6 and 6. Meaning if I reached in with a voltmeter right here and right here, I'd measure 6 volts. Here and here, 6 volts. I know that that bulb C is brighter than A or B. Brighter bulbs, more volts. And so that bulb C has to have greater than 6 volts. Again, any path has to be zero-sum game. It has to add up to 12. Here's one path all the way through C and then through D and then back to the battery. That means the voltage across C and the voltage across D have to add up to 12. If C is more than 6, D has to be less than 6. And so now I can easily compare these two bulbs. This one has 6 volts. This one has less than 6 volts. This will be dimmer, brighter. Got it? Okay. We also found last day that this voltage model gives us the reason that branches that are parallel across the battery, remember there's two flavors of parallel? These two bulbs, B and C, are just regular old parallel. Nothing special about that. This branch in this little red box is parallel across the battery. That's a special kind of parallel to this box here in this red box. And so that means they are independent of each other. Well, now we know why. They each have direct connections to the battery. They each always have 12 volts across them. I can do anything I want to bulb D. I can bust it with a hammer. I still got to have 12 volts across this branch. So it just doesn't care. As soon as I put that indicator bulb there, they are no longer independent. Because as soon as I make a change in this box over here, that affects the brightness of the indicator bulb. That's going to affect the share of the 12 volts that this box here has left. So now the two boxes are no longer independent. Again, with our current model, we were not able to predict what would happen to bulb A when I close this switch. With a voltage model, it becomes trivial. I close the switch, see it? There it goes. Technology. You know, before you would have had to do that with chalk and you'd get all dirty. Just. Okay, what's that going to do to the current through the battery? I just closed a switch that added a path. Yeah, the resistance of the circuit as a whole went down, the current through the battery went up, and if I look at that indicator bulb, if the current through the battery went up, so did its current. That means the indicator bulb just got brighter. Brighter bulbs, more volts. And so if I look at the voltage across that indicator bulb, just went up. Well, now the real question I wanted to know was what happens to bulb A? And instead of asking, does it get brighter, does it get dimmer, I could ask, does its voltage go up or go down? Again, it's a zero-sum game. The voltage across the indicator bulb plus the voltage across bulb A plus the voltage across bulb B have to add up to the voltage of the battery. Let's call that 12 volts. If the indicator bulb just got brighter, its voltage went up. Whatever A does, B has to do. B gets exactly half the current through A. So that means the only way I can keep this 12 volts when this gets bigger is for these things to get smaller. So A and B and indeed C all get dimmer by closing that switch. Would you check that your neighbor is on the bus with the voltage model? Okay. Last day we talked about the fact that we couldn't compare D and E with the current model, and we did it successfully with the voltage model, and we've already done that. I'm going to not drag you through that again. We didn't get to this. When we put that connecting wire from one side of B to the other side of B, we short B out. We found that A got brighter, we found that D got brighter, B went out, but we couldn't predict what happened to bulb C. With the current model, we had one of those conundrums. Well, now with the voltage model, it's easy enough to answer. We just pick any path that goes through from one side of the battery to the other that includes bulb C. For example, the path that goes through A, and then through C, and then through E. That's one path all the way from one side of the battery to the other, so it has to add up to the battery voltage. Again, let's just give it a number, 12 volts. If putting that wire across from one side to B to the other side of B makes A get brighter, C and E have to get dimmer. Oh, because whatever flows through C, when it gets through here, it splits. And so whatever C does, if it gets dimmer, E has to get dimmer because it's getting exactly half of the current through C. I'm sorry? Yes, F would also get dimmer. I could have chosen a path A, C, F and made the same argument. Okay? E and F would be dimmer than C by both models. They would be equal to each other. Okay? They would be dimmer. Now be careful with the half as bright because bulbs are very complicated beasts. They're not linear. You can't say twice the current, twice the brightness. You can say more, you can say less. Other questions? Other questions?
Can you just say that you decrease the resistance on the left side so the
Ah.
you're going to receive more current on the left side?
Yeah, okay, the question is, can't I just say, well, I just decreased the resistance on the left side, more of the current's going to go on the left side, which means left for the right side. Doesn't that seem obvious? That would work if the battery always gave the same amount of current. Does it? No. By putting this up here, I do change the splitting ratio here. More than half goes this way, and less than half goes that way. But the current that we're splitting goes up. So if you try to answer what happens to C using the current model, you'll get 0 points. Okay? The current model says that, well, C gets a smaller share of a larger pizza. Are you going to claim that's more or less? Okay. You know, and that's worth 0 points, and that's something. No. Okay. The voltage model tells us that voltage divides for elements in the circuit that are in series with each other. Things that share the same current. If those two things that are in series with each other have the same resistance, they will divide that voltage 50-50, evenly. If, on the other hand, they are not equal, then the voltage drop is greater across the, would this be greater or lesser R? The box that has the greater or the lesser R gets the bigger oomph from the battery to get the current through it. Greater R. The key idea here is they're in series. Each second that goes by, that battery's got to stuff the same number of coulombs through box A as it stuffs through box B. It's just harder to get coulombs through box A than it is through box B because it's got more resistance. And so the oomph of the battery, that's the voltage, has to be divided in such a way that more of the oomph is expended getting coulombs across box A. You have some tutorial homework that is due Tuesday, not Wednesday, Tuesday at 5 o'clock. We don't have class on Monday. Let's talk about it now. This is the hardest problem on the homework. You go ahead and get that out if you'd like. It's on the last page. A circuit diagram does not, I repeat, does not tell you where the wires are laying on the table. Circuit diagram tells you what is attached to what. And you'll notice that I've drawn it differently than it's drawn in your tutorial. But in my diagram, 6 is still connected to 4 and 5. Is that the way it is in yours? 4 and 5 are both connected to 2 and 3. Is that the way it is in yours? 1's connected to 2. You can redraw those in such a way that it's clear what's in series with what. Now, if I use the current model to rank these bulbs, it's really quite simple. I just B the river. I can go clockwise. I can go counterclockwise. In this case, it might be easier to go counterclockwise. I start at this negative end of the battery, and I just pretend I'm the river going around. How much of the current through the battery goes through 6? All of it. Then I split here, 50-50 or some other way. 50-50. Then it comes back together, and I split again, 50-50 or some other way. Some other way. And so the ranking that I have to get here with the current model I do. I'm going to have 6 is going to be brighter than 3, which is brighter than 4 equals 5, is brighter than 1 equals 2. Everyone with me? 6 gets all of the current. 3 gets more than half of the current. 4 gets half of the current. 5 gets half of the current. 2 gets less than half of the current. And it's in series with 1. Now, what if you had to use the voltage model? What if on the midterm I said, you know what? You have to solve this problem on this page with only your voltage model. I'm tying your left hand behind your back. All you got left is your right hand. Could you do it? Could you do it? The first thing you do when you are using the voltage model to solve for the ranking of bulbs is you decide what's in series with what and put a box around those things that are in series. What's in series? Bulb 6 is in series with, is it in series with bulb 4? 4 and 5 together. All the current that goes through 6 has to go through that network of 4 and 5 together. All the current through 6 doesn't have to go through 4, so they're not in series. But the network is in series. And it's also in series with that network. Once you have your boxes drawn around everything in series, you ask yourself, which box is hardest to get through? Which box has the most resistance? Which box would that be, folks? Top one, it's got 3. Yeah. This is why it's so important, those little games we played, ranking resistance, which one has more resistance. If you can't tell which of those boxes has the most resistance, you can't use the current model, you can't use the voltage model. You're modelless. Okay? So what I do is I ask myself, what would I have to add to this to turn it into that? This bulb, I clipped it on, it's in parallel, so this has less resistance than that. What would I have to add to this network to turn it into that network? This bulb, did I use scissors? I did. So this one has more resistance than that one. And I could make the same argument why this one has less than that. Bottom line is, the bottom one has the most, and then the top one has the second most, and the middle one has the least. It's Papa Bear, Mama Bear, Baby Bear. Okay. Now, does the voltage model give the same answer as the current model? The voltage model says whichever box has the most resistance is going to have the biggest share of the volts across it. That suggests that we're going to have the biggest number of volts across this box. Which bulb's going to be brightest with the voltage model? 6. Second brightest? 3, because it's got all the volts across this box here. And the next brightest would be, turns out you'd like to say 4 and 5 because you know what the right answer is. But the voltage model actually breaks down here, doesn't it? I know that there's more volts across this top box than this bottom box, right? But I don't know how much more. I know that 4 gets all the volts across this middle box. Bulb 2 gets what share of the volts across its box? If there's 5 volts, I'm making that number up, if there's 5 volts across that top box, how many volts are there across 3? Shout it out. 5. How many across 2? 2.5. Okay? So 2 is only getting half the volts across its box. 4 is getting all the volts across its. So I'm comparing all of a small pizza to half of a large pizza. The voltage model fails. Good thing I had the current model. Now, in your homework, they take away bulb 1 and leave the empty socket, big gaping hole there. And they ask what happens to the bulbs in the circuit. First of all, what happens to bulb 2? It goes out. There's no path through 2. It goes dark. So what happens to the number of volts across 2? I got a dark bulb, completely black, dark, out. How many volts across it? Put the voltmeter across, what do I get? 0. A dark bulb, 0 volts. Okay? What happened to the resistance inside the boxes? Did the resistance in this box change? This box? This box? Yeah, this box just went up. It now has the same resistance as the bottom box. Now, the question is, what happens to the resistance in the last box? Did it change? It's still the same. It's just one bulb. If the resistance of that box did not change, should the voltage across that box change? Let's switch hats for a minute. Use the current model. You removed a path. Is bulb 6 going to get brighter, dimmer, or stay the same? You remove a path. Resistance goes up. Current through the battery goes down. It's an indicator bulb. So we know that 6 has to get dimmer. The question is not what happened to the resistance of the box 6 is in, but what happened to 6's share of the total resistance? Let me see if I can clarify this with an example. Suppose you have a 12-volt battery hooked across these 2 bulbs in series, a 2 ohm and a 4 ohm. That 12 volts has to be divided amongst the 2 and the 4 ohm resistors. How would it get divided? How many volts across here? It's got to add up to 12. Should it be 6 and 6? If these were equal resistances, it should be. But this is twice the resistance of that. So I got to have 4 and 8. Okay? You got to work on that. Now, we are tempted to say, with that little exercise, the greater the resistance, the greater the voltage. The greater the resistance, the greater the voltage. But what if I say there's another branch here, and this resistor is 200 ohms? if I use that statement, the greater the resistance, the greater the voltage, well, 2 ohms got 4 volts. Hey, this is 100 times bigger resistance. So it should have 400 volts across it, right? Pretty impressive for a 12-volt battery, wouldn't you say? How many volts are there across that? Is there anything you'd like to ask me? Yeah, what's this? What's this? What if I told you that that's also a 200 ohm resistor? What would it be? How would you divide it up? 6 and 6. So here's the key idea. The greater the resistance, the greater the voltage is wrong. You have to complete your sentence. The greater the share of the total resistance, the greater the share of the total voltage. The greater the share of the total resistance, the greater the share of the total resistance. This resistor here represents half of the resistance in this independent branch. It gets half of the total 12 volts of the battery. This 2 ohm resistor represents 1/3 of the total resistance in this circuit and gets 1/3 of the total of 12 volts. Okay? Now both of these branches get 12 volts across them. What about the current through them? Is it going to be the same through both? Be the river, it comes up there and it sees one branch with 6 ohms and one with 400 ohms. How's it going to divide? 50-50 or some other way? Yeah, I'm going to get a great big rush of current through this one, a little trickle of current through that one there. So let's go back here. When I take out bulb 1, the resistance of this box containing 6 does not change. However, its share of the total resistance just went down. It no longer represents as big a share of the total resistance in the circuit. And so its share of the voltage of the battery goes down, and the voltage model predicts that 6 will get dimmer. Okay? Questions? So 6 gets dimmer. Now if I use the current model, we already did this. You remove a path, the resistance goes up. Current through the battery decreases, and 6 is an indicator. What happens to the first box's share of the total resistance? Go up, down, or stay the same? It went up. So what happens to the brightness of bulb 3? Another way of asking it is, what just happened to the voltage across bulb 3? Yeah, its share of the total resistance went up, and so its voltage went up. It got brighter. Now, let's say that the voltage across bulb, or this box here, the top box, let's say that that just changed from, I'm making these numbers up, it changed from 5 to 7. How many volts does that mean is across this bulb? There's 7 across the whole box, from top to bottom. How many across this? 7. Okay? If the 7 volts is from the top of the box to the bottom box, across any path. How many volts across this dark bulb? 0. Where's the 7 volts on this path? Let me... Let's say I've got 12 volt battery. I've got 100 ohms and I've got 100 ohms. This is going to give me 6 volts and 6 volts. If I change this one to 100 million ohms, how do I split up the 12 volts here? Yeah, this is going to get 0.001 volts, and this is going to get essentially 11.999 volts. What if I make this even bigger? I just keep on putting zeros here. Do I eventually get where this gets 12 and this gets 0? Yes. When this represents virtually all of the resistance in the circuit, it gets virtually all of the 12 volts in that circuit. And so when I get an infinite resistance, like a gap, that then gets all of the voltage. Let's see if that's true. I have here I've got this circuit that we know and love. We've seen this before. And if I measure this across this bulb, if I measure the voltage across this bulb, I get what on the reading? 12. Here? What does it say? 12. Okay, now I'm going to open this switch. I still get 12 across here, don't I? What across this one? It's a dark bulb. What were you expecting? Nothing. I told you any path from one side of the battery to the other has to add up to 12. This is contributing 0 of it. What do I get when I put it across here? 12? All right. Is it 12? I knew it was. Okay. So that pretest you just took, the answer to the second part was 12. Okay, we still got 5 minutes. Let me make sure that you understand that pretest before we leave. In your packet, I've given you a summary page that kind of clears up what happens when things are in series and parallel. Essentially, it says this. When two things are in parallel, the current splits and the voltage is the same across both parallel branches. When two elements are in series, the current is the same and the voltage divides between those two elements. Let's not go here. Nope, we're going here. You were told that the voltage across this 6 ohm resistor was exactly 4 volts. And you were asked, first of all, how many volts are there across this 3 ohm resistor? And the answer shouted out, 4 volts. 4 volts. These are in parallel with each other. Any branches in parallel have to have the same voltage across them. So that would be 4 volts. I've already used 4 volts and 4 volts. That's, I'm up to 8. How many across here? Yeah, I was trying to trick you, wasn't I? The answer's 8. Because any single path from one side of the battery to the other has to add up to 12. This path has to add up to 12, and this path has to add up to 12. I still got 2 minutes, folks. And this is important. This is a way you can lose a whole bucket of points on the exam. Did the 8 volts split in half at the node and 4 of the volts go one way and 4 of the volts go the other way? Did they? No. No, volts don't flow. On the midterm, any sentence that uses the word volts and through in the same sentence, the number of volts through bulb A, for example, will receive 0 points. There are no volts that flow through anything. We have voltage across things, the voltage across bulb A. The current goes through bulb A. Voltage across, current through. The volts don't flow, they push the flow. I'm going to twist this a little bit. Suppose I add another resistor there, and suppose I tell you that the voltage there is 9.6. What would the voltage here be? it would have to be 2.4. And likewise, if I measured across here, it would be 2.4. Across here, it would be 2.4. Indeed, when I reach in with my voltmeter from here to here, I'm measuring the pressure difference between those 2 points along any path between them. Okay? Are there questions? Okay, please. Try to work this problem before you come back on Wednesday.